to this session. The first speaker of this session is Xiongfeng Ma from Tsinghua University in Beijing, China. His topic is fidelity measure of a multipartite state. So feel free to start.
All right. Okay, thanks. First of all, I'd like to thank the organizers to put up this very nice workshop in this very hard time. So I hope that the next time we can meet in person. All right, so today my talk will be about the fidelity measure of a multipartite state. So we have a few papers on this work, so together with my graduate students. So first, I will give a very brief introduction about the genuine multipartite entanglement and entanglement weightiness. Then I will talk about the permutation invariant state. So how can we get the fidelity of a permutation invariant state? After that, I will talk about another work. Similarly, I want to get the fidelity of the state, but the state is graph state. We know that in general, graph state is not permutation invariant. Finally, I draw the conclusion. Introduction. So we know that since the EPR paradox, we come across with the John Bell come across with the Bell's inequality. Sometimes we also call it the Bell non-locality. And then we eventually reach to the concept of the entanglement, and the entanglement is widely discovered in the nature, like for example in the photonic system, or the spin of the electrons. So it's not very old concept, and also it's not very fancy experiment. Actually, it's been around like more than 50 years, 70 years ago. So we already observed this entanglement. Although at that time we don't know it is entanglement. We just feel like it's some correlation. Okay. And then I will talk about what's entanglement weightiness. Okay, so that's pretty much the background. So I assume that everyone here are quite familiar with the entanglement. Okay. Definition of the entanglement. So let's look at the definition of the entanglement. Let's start with the simple bipartite entangled state. So we know that suppose we have two systems, A and B. And then if a state can be written in this form, so everyone can see my mouse, right? Michelle, is my mouse?
Yes.
It's visible. Okay, that's very good. So if a state can be written in this form, so if we look at the row A tends to row B, so this is we call a product state. If a state can be written as a linear combination of the product state, then we call it a separable state. Okay. Obviously, by this definition, all the separable states form a convex set, right? So any two separable, if you combine two separable states together, it's still a separable state. Okay, so that's in this figure. Okay, and then any state cannot be written in this form. We call it entangled state. So we know that in all the state, quantum states form a convex set, and then separable state form a convex set. As a result, entangled state, the set of entangled state is not convex. Okay, so so for example, let's give one very quick example. It's like for example, one state is like 0, 0 plus 1, 1. We call the Bell state, right? Bell state, this triplet Bell state cannot be written in this form. Okay, this is a very easy example. And then if we combine two entangled states together, we might get a separable state. Again, we just use two Bell states. If we mix two Bell states with 50-50 probability, then we get a separable state. Okay, so this is quite standard quantum information 101. And then we say that how can we in experiment, how can we verify a state is entangled or not? Okay, so we use we call it entanglement weightiness, so which is observable W, and then the measurement outcome for this W is all positive for all. It's positive for all separable states, but for some entangled state, it's negative. So obviously, by the first criteria, so once you measure some state, if it gets negative results, then it must be entangled. Okay. So in this figure, it means that okay. So so that's the entanglement weightiness. Okay, two entanglement weightiness examples, W1 and W2. So on the right hand side, it is less than 0. On the left hand side, it's non-negative. So the whole separable state set is on the left hand side. So we can see from this figure, If you find that it's a negative, it must be on this side. It is entangled. Okay, so that's a basic idea of the entanglement weightiness, which we will use in this talk. All right, so let me give one very simple example, which is widely used as entanglement weightiness. Okay, let's say psi minus is 0, 1 minus 0, 1, 0. So this is a singular state. We know this is a Bell state. It is entangled state. So we just we use a weightiness at this form. So essentially it has two parts. So the first part is just identity. So it's 1/2. It's measure any state, you get a constant of 1/2. And then this state is the projection to this singlet state. So which essentially measures the fidelity of this singlet state. And then, so this idea of this kind of entanglement weightiness means that, okay, so suppose you have a target state here. So which is psi minus. And then you measure the fidelity between your unknown state and the psi minus. And then if the fidelity is very close to 1, so basically it means that it's the state is around this state. It's not too far away from this state. They actually be entangled because this psi minus should be quite far away from the separable state set. So that's a basic idea. Okay. And then in general, this, if we look at the W in this form, it is a joint. It is a joint measurement, right? And then we can decompose it into local observables. So we know that this one equals to this one. Okay. So this is mathematically equal. So then, in order to measure this W, we can just measure locally with this x-axis measurement plus y-y measurement plus z-z measurement. Then what do we get? So that's the W. So this is very important because in general, we do not. So in the experiment, we do not intend to measure a joint measurement because joint measurement normally involves some complicated operations. Especially when we talk about the multipartite state, in general it's very complicated. But local measurement normally can be done easily. Okay, so essentially for this one, how many local measurement settings we need is 3, right? X-axis, y-y, z-z, right? So this I, we don't need to measure I, right? So that's a basic idea. So essentially, so this is a very basic idea about the entanglement weightiness. So one way to measure, one way to do the to witness the entanglement, we just measure the fidelity of an integral state. If its fidelity is high enough, then we can prove that it is integral state. So that's a basic idea of this talk. Okay. Oh, by the way, feel free to stop me and ask any questions. Okay. So this is the basics of the this talk. Now we move on to a little bit more parties, tripartite tripartite case. Okay, so we know that's the so there were lots of examples of the three qubit entanglement state, entangled state. For example, GHZ state 0, 0, 0 plus 1, 1, 1. W state 0, 0, 1 plus 1, 0, 1, 0 plus 1, 0, 0. Okay, so that's two very typical tripartite entangled state. So so we might follow the similar definition with the bipartite state case. We know that's so this kind of state is the product state, right? Rho A tends rho B tends rho C. So that's a product state. Any linear combination of the product state is still a separable state, right? So that's pretty much the same definition as the bipartite case. So for this state, we call the fully separable state. It's contradicts to that the states like this one. For example, if we have states like psi 5 plus AB is in the 5 plus and the C is a tensor product form. So we know that this state, it is entangled state, but it's not, we call it, it's not genuinely entangled state, right? It's not genuine tripartite state. It's like this figure, A and B, they are entangled, but C is separable, right? It's product state, it's separable, right? So of course, this state cannot be written in this form. So it's not a fully separable state. So we want to study that is there any state that is we call the genuinely entangled state, which cannot be written in this form, bipartite entangled state form. Okay, so that's the idea. All right, so genuine tripartite entangled state. So we know that it can be for three-party cases simple. So it's rho AB tensor rho C, rho AC tensor rho B, rho BC tensor rho A. So that's all product state. And the linear combination of all these we call a biseparable state. This is we call a biseparable state. Okay. So this is a biproduct state. If a state can be written as a linear combination of the biproduct state, it is a biseparable state. Okay. All right. So that's a simple definition. Any state cannot be written in this form, biseparable state form. Then we call it genuine multipartite entanglement. Okay. All right. So I have to remind you that the pairwise entangled state does not mean genuinely entangled. So let me give just one example. So it means that if A and B entangled, B and C entangled, A and C entangled, does not imply A, B, C, they are genuinely entangled. Okay, so pairwise entanglement does not imply genuine entanglement. Okay, like one simple example will be this one. Okay, so from here, so this state, so this 5 plus means that this is 0, 0 plus 1, 1 is Bell state, and it's density matrix form. Okay, so obviously this state, it is a biseparable state, right? It can be written in this form, right? But you can quickly check that this state is pairwise entangled. Okay, so in this figure, so in the middle it's the fully separable state, and then here we have the biseparable state 3 and the 2-1 system, and then we have another biseparable biproduct state in this form, and then there's also pairwise entangled state, but not genuine entangled state. Outside is the genuine entangled state. Okay, in this form. So from here we can see that just with three tripartite case, it's already a little bit complicated. Okay, and we know that there's famous Sivak-Zoller results, right? So for tripartite qubit case, it's like three qubit case. There are 2 equivalent classes via stochastic LCC, right? So there are W-like or GH-like, right? Okay, but in general, when the number of parties go to bigger, like 4, 5, then we don't have such kind of nice classification of this entangled state. Okay, so now let's go to the M-partite case. Okay, so again, let's start with the simple case, which is fully separable state. Okay, fully separable state is written in this form. Okay, so basically it's just a product state and a linear combination of the product state. Okay, so this is the AJ is the party. Okay, AJ J equals 1 to M. Okay, it's M party. Okay, so they are all separable. Okay. Similarly, we can also define we call the biseparable state. Okay, biseparable state we written in this form. Okay, so again, it's a product state. So basically, it's like we separate this M party. So this A and A bar. So this mathematical form of A and A bar, it means that A and A bar, they form the full set, the index of the 1, 2, 3 to M. So basically, it's like A and A bar is like you pick up some party, A bar pick up the rest. Okay, so if you can written in this form, we call the product state. And then if we have a linear combination of this one, it's a biseparable state. For GME, any state cannot be written. Any state cannot be written in this form. It is a genuine entangled state. Okay, genuine entangled state. Okay, and also there's some wider belief that the genuine entangled state is a very fundamental key resource for quantum advantage. For example, if we look at the recent Ivan Deutsch's perspective paper on the PRX quantum, the first issue, then it says that we have some evidence to show that the genuinely entangled state is very hard to simulate. Okay. In general, it's very hard to simulate. From there, we can see that it's widely believed that it's a key resource, one of the key resources for quantum advantage. And also in a way, for example, we have nowadays we have in quantum system, like we have a superconducting system, we have ion trap system, we have quantum optics system. So for different kind of physical systems, Then, so people comparing that's which system is better for quantum computing or quantum information processing. One criterion we can compare with different systems is the number of systems, number of genuinely multipartite entangled systems. So basically, how many systems you can, let's just say qubits, or how many qubits you can entangle together genuinely. Okay. So this is we can think of GME is some kind of benchmark or the score we can compare among different physical systems. Okay, so this is very important. So let's look at entanglements. Of course, so that previous the definition in the previous slides, we have two extreme cases. One is the fully separable state. One is the biseparable state. And then we go to the genuinely entangled state. Actually, then we also can define. We can also define we call the M separable state. So we can divide this index M parties. We can divide M parties into M partitions. Okay, M disjoint partitions. And then if they can return in this, of course, non-empty M disjoint partitions, and then you can return if the states can be written in product form, linear combination of the product form, then we call it M separable state. Okay, so this is a very natural definition. Obviously, this fully separable state is the N separable state. Okay, N separable state. Genuinely entangled state is one separable state, right? One separable state. So basically, so that's the entanglement hierarchy. Okay, that's the entanglement hierarchy, right? So obviously, two separable states contains any M separable states, right? Okay. So from there we can check out the entanglement structure. One question is as to why we are interested in entanglement structure. So actually from the experiment, it's quite interesting because suppose we have a very large system, let's say 100 qubits. Then because of a counter, so normally it's like it's a big chip, right? It's a big chip, so it contains 100 qubits. But maybe some of the qubits it's not maybe could be due to the design or maybe due to the manufacturer. So some of the qubits they are not as good as the other qubits. So we want to see that when we entangle them together, if we can look at the entanglement structure, we can roughly figure out that where these imperfections come from, which qubits they are bad. So we can figure them out, and also sometimes we can also figure out that what's wrong with the, for example, if you design a quantum circuit and then you are supposed to get one state, but it should be let's say it's genuinely entangled, but what you get is only M separable state. Then you can figure out where the separability come from, and then you can figure out what's wrong. And then you can go back to the experiment again and then check the circuits again. So this is entanglement structure is quite rather important. And also it's very, very complicated in general. Okay, so today I will focus on the genuinely multipartite entanglement. Okay, so similar to the entanglement witness, so the bipartite entanglement witness, we can also have this genuine multipartite entanglement witness. Okay. So it's similar because of this convexity of the two separable states. So we have a witness. So it should be non-negative for all biseparable states, sigma. And for some genuinely entangled state, it is negative. Okay, so that's the definition. Okay, so this definition is pretty much the same as the bipartite entanglement witness. It's a natural extension. All right, so again, there's one typical way to construct GME is that so suppose we know that's like a state like a GHZ state, 000 plus 111. So this is a genuinely entangled state. It's quite easy to prove that. And now how to construct GME witness? Then we just measure the fidelity between this state, between the unknown state and the GHZ state. If the fidelity is big enough, it's very close to 1. Then we suspect that it is entangled state. Okay, so we have this one, and then this alpha will be just go through all the biseparable state, and then check out that what's the maximum fidelity for a biseparable state you can achieve with the GHZ state. In this case, it's 0.5, 1/2. Okay. So if you get a fidelity larger than 1/2, it must be genuinely entangled state. Okay. Okay, so this is the easy part. So this is the easy part. This is so this is a natural extension from the bipartite EW to the GME EW. Okay. And the hard part is how can we decompose states like this, observables like this one, W. So this is a joint. This is a joint measurement, right? Joint measurement, as I just said, joint measurement normally is hard. In that experiment, in general, it's very hard. So how can we decompose into like what we did with the singlet state? How can we decompose into local measurements, like local measurements? Okay, so one idea, so it is feasible. We can do that. Definitely, we can do that because of the tomography. We can always decompose this state like this one into the local observables with tomography, right? Of course, tomography is not efficient. It's exponential in n. So in general, we need 3 to the n of local observables to construct a fidelity measure. So in this talk, my main objective is try to lower we call the local measurement setting complexity. So we want to lower this number of local observables, okay? So that it's not exponentially in n, okay? All right. So of course, it cannot be done generally. In general, we need, for the tomography, we really need exponentially number of local observables. But for some special states, like especially for those states we are interested in, like permutation invariant state, like a symmetric state, or later on I will also talk about the graph state. For those states, we can do it. We can do it with sufficiently low number of local observables. All right, so I think I have 14 minutes, so I think I still have time. All right, so let me first start with the definition of the permutation invariant state. So there's one we call the symmetric state. A symmetric state, the definition is very simple. So this pi is a permutation. Think about it as a p of pi. This is a unitary transformation. Just permute two of the so this is the permutation of the parties. Okay, if a state is the same, it's invariant under any permutation, we call the symmetric state. Okay. All right. So what's the permutation invariant state? It's just similar to this one, but it's in the density matrix form. Okay. Obviously, any symmetric state is a permutation invariant state. But in general, permutation invariant state, it is not symmetric state. Let me give one very simple counterexample. It's the singlet state 0, 1, minus 1, 0. So we know that if you change these two parties, you will get a minus sign outside, right? So it's not a symmetric state, but it's a permutation invariant state. So this extra overall phase is not important in physics. So from here we can see that the permutation invariant state and the symmetric state, they are pretty much the same set, pretty much the same. Okay, from physics point of view, pretty much the same. Okay. All right, so there are many examples. One example would be GHZ state. Obviously, it's a permutation invariant state. It's a symmetric state, and also W state, and also Dix state. Dix state is a definition that's a W state is the Dix state with the it's a special case of Dix state with m equals 1. So basically, it's instead of just only one here in each state, you have m ones in each state. So that's a Dix state. Again, they are all symmetric states. Okay. So in this talk, we won't really distinguish the symmetric state and the permutation invariant state because in this work, pretty much they are the same. Okay, they behave the same similarly. Because we will talk about the mostly we'll talk about the pure state. Okay, so we talk about we focus on this kind of symmetric state. So keep in mind that what do we need? What we need is that I want to measure this GME witness in this form. Okay, so this alpha is just some constant, and we want to decompose this we call the fidelity observable. We want to decompose this fidelity observable into local observables in this form. Okay, Okay, so that's the main part. So we really want to make sure that this summation is not too many terms here, because each term correspond to in the experiment will correspond to one measurement. I don't want to measure too many times. So in general, with the tomography, it's the number of terms is 3 to the n. That's exponentially amount. But if we talk about that as a symmetric state projection, suppose this state is symmetric, so permutation invariant state. Okay, I will use these two words like with the same meaning. I will just assume they are the same. Okay, they are slightly different as I defined in the previous slide. Okay, so if we talk about the symmetric state, then we know that we can, because the number of free parameters in this state is much smaller than a general side, right? So can we do more efficiently? Can we do better than 3 to the n? So that's the question. All right, let's look at the how many parameters we have in the symmetric subspace. Okay. All right, so let's define the symmetric state subspace. Okay, in this form. Okay, so there are two different equivalent ways to define it. One is this one. So this it's a set of the state such that it's a permutation invariant. Okay, so this is basically the definition of the symmetric subspace, right? Symmetric subspace. So this means that this state for any permutation, it is the same. It's invariant. Okay. Keep in mind that this I write down this permutation in a little bit sloppy way. So this is just means that it's kind of a unitary transformation of permutation between two parties. Okay, and a few parties, any parties. All right. So another definition will be this one. So it's just a state tensor to the n. Obviously, this state it is a symmetric state, right? Because for all the parties, they exist in the same state. And then you use this state to span the space. It is a symmetric state. Okay. I will skip the proof, and it's just we just use some linear algebra. We can quickly prove that. Okay. So there are two equivalent definitions of the symmetric subspace. Let's start with the first one. First one is simple. All right. So let's look at the orthogonal basis. Okay. It can be written in this form. So this is an orthogonal basis. All right. So let me explain a little bit of this state. So we talk about that d-dimensional, d-dimensional hyperspace. We have m-party. Okay, m-party, d-dimensional hyperspace. So this state is, if we look at it without this summation, if we look at this state, it's a product state. It's a product state. So actually, any product state. So in the computational basis, it can be written in this form, right? Okay. So this is 0, 1 to the d minus 1. So all the I0, I1, ID minus 1. So that's the summation of this this state. Summation of this I labels is equal to m. Okay. All the i's should be non-negative. So it's they are integers. They are natural numbers. They are natural numbers. Ik, they are natural numbers. Okay. All right. So and then you do the permutation. So that's a computational base product state in the computational basis, and and then you do the permutation, run all the permutation. So this summation takes all the permutation, and then obviously we can see that all these states between different kind of Ik, the states they are orthogonal, right? Because this is defined in the computational basis. So they are orthogonal. First of all, they are orthogonal, and also you can prove that you can quickly prove that this is by definition it's a basis. It's an orthogonal basis for this first definition. Okay, for the symmetric subspace. Okay, so you can also quickly check that okay, for a special case when d equals 2, qubits case, then the state looks like this one. Okay, look at this one. So which essentially is a Dix state. It's a Dix state. So we can see that any symmetric symmetric subspace state it's basically it's just it's a linear combination of the Dix state. Okay, so that's the basic idea. So if you look at this state, now let's count the number of bases states. So because the summation of all the Ik equals to m, and the Ik should be greater or equal than 0. It's a natural number. So we can quickly see that the dimension of this symmetric subspace is the m plus d minus 1 choose n, right? So it's this one. Okay. All right, so that's the dimension of the symmetric subspace. So we expect that we can do better in this way. Okay, All right, so now let's look at another decomposition. So as I said, there's another definition of the symmetric subspace. So this the second definition, equivalent to the second definition, is phi to the n, tensor to the n. And then, so we want to also find another, we call the orthogonal product form basis. Okay, so this is this actually it is being non-orthogonal. Okay, so in this case, it's non-orthogonal. Later on, we can make it orthogonal later on. Okay, so let's start with the non-orthogonal one. So this state, so this is the state. It's a single system. It's a single party state. Okay, and then tensor to the n, tensor to the n. Obviously, this is a symmetric state. Okay, so we also have the this A0, A1 to the A D minus 1. So that's the coefficient for this 0, 1, D minus 1, this computational basis. And then there's a J0, J1, J of the D minus 1. So that's the coefficient for different state. Okay, so we can write down this A into this matrix form. Okay, matrix form. Okay, for each this for column. For each this column correspond to one state here, correspond to one state in this basis. Okay, so how many states we have? M. We have m plus 1 here. We have m plus 1 here. Okay, so and the dimension is d. Okay. Okay, so actually, so with some linear algebra, we can quickly show that if we choose the first row equals 1, and then all the columns are different. If we choose A such that all the columns they are different, then they are linearly independent. Okay, so that has been shown in this paper and also in our work as well. So they are linearly independent. Okay, so now the question is yes, we can use this one to form a product form basis. Okay, and then so let's with this one. Okay, so then how many linearly independent states we have, because summation of the JK equals to M, right? So we can show that because of this summation. So this is very similar to the summation of the IK equals to N. So how many A's we can choose here? It's again, so the number is the D plus M plus D minus 1 choose N, right? So then with this one, we can find so many so we call it so many bases, right? So many bases, right? And then from the previous this slide, we already know that the space, the dimension of the space is this large. If you can use another form to find so many linearly independent states, then that's already a non-orthogonal basis, right? So that's the basic idea of this one. Okay, so now we want to show that so it's okay. Keep in mind that this how many states we have? M plus D minus 1 choose N. Okay, so then that's a product state form. So of course, each product state corresponds to one local measurement, right? Okay. All right. So now the question is that we want to measure the fidelity between the previous states of rho and the permutation invariant state. So we want to show that we have a theorem show that so this projection, this fidelity observable can be decomposed to m plus 2 choose 2 local measurement settings. Okay. Or for some special cases like a GHZ state, we can even reduce this. Can be further reduced. Okay. All right. So first we decompose this projector into local operators. Okay, local operators. Let's start with the polygroup element. Okay, so there's the G1 stands for the single qubit polygroup. Okay, sigma X, sigma Y, sigma Z. Okay, so let's look at so think about that. This is a basis. This is a basis. Think about that. Use this basis to form a symmetric m-party subspace. So think about that. We have poly operators. How many poly operators we have? We have m poly operators, and then we use a symmetric. We use a symmetric subspace like used to represent this one. Okay, let me look at the definition. Okay, more closely. Okay, so there's m. M is an operator in the so m-partite operator. Okay, m-partite operator. Okay. So think about that. The M is a polygroup. one special case with n is a Pauli operator. Okay, n-partite Pauli operator. Okay, of course this is in general it's a combination of the Pauli operators. Okay, it's symmetric, so any permutation won't change this n. Okay, all right. So we have n-partite Pauli operator, and then we have if you do any permutation, it's the same. Okay, so we have this we call the symmetric subspace for the Pauli group. So that this operator can be written in this form. Right? We can find the orthogonal basis in this form. Right? Okay, with all permutation. Okay, so this orthogonal is defined as the Hilbert-Schmidt inner product form. All right. So we know that they can also span in this form, right? A to the n, right? A to the n. Okay. A is the single qubit operator. Single qubit operator. So we know that it's not hard to see that this G1 is G1 so the symmetric subspace of G1 is also isomorphic to the symmetric subspace of R4, right? Real number 4, right? So it has a dimension of the n plus 3 to 3, right? Okay, with this one, right? Okay, so that means that's which size of this subspace? It is n plus 3 to 3. Okay, so that's what we get. Okay, so we can decompose any symmetric operators, n-partite operators into this form, product form. We call the local observable form. And then how many basis states we have? N plus 3, choose 3. So each state is in this form, right? But we don't really need to measure I, right? We don't really need to measure I. So in order to measure this one, it's sufficient to measure. Just so if we lose this I, then it's sufficient to measure this one, right? Of course, not only measure this one and also measure n-1, n-2, etc. Right? We can use this operator to inform the measurement outcome of this local observable, right? And then we reduce the n plus 3, choose 3, reduce down to the n plus 2, choose 2. Okay, so that's our main result. And also for some special cases like a W state and a GH state, we can do better. Okay, so do better. So like 2n-1 and n plus 1. So those two results it's also appeared more than 10 years ago by Gunner's group. Okay, so for this state, we need a little bit more observables, like times n. Okay, when n is a small number, then it's still linear with n. Okay. In addition to this, we call the upper bound. So that's we really construct this fidelity measure with so many local observables. We also show that actually there's a lower bound. If you want to really measure this fidelity accurately, then there's also exists this kind of lower bound. Okay, I will skip the details. Due to time limits, I really don't have time for the graph state. Okay, so the graph states, the good thing about graph states is that's the okay, I'll quickly show you just one result. Is that's the okay? So the graph state, if you take the bipartite state in this case, so the Schmidt number is always the spectrum is always flat. It's always a 1 over R. So then if you use this state to find this alpha, like the fidelity between biseparable state and the G, we can. So this one, you don't really need to do this one. It's always R 1 over R. Okay, it's always a 1 over. So that's a basic idea to calculate the alpha. And then for graph states, we don't really calculate the fidelity accurately. So previously in the symmetric state, we really calculated the fidelity accurately. In this one, we only calculate the lower bound. Due to time limits, I have to skip it to the end. Yeah, probably I spent too much time in the introduction. So in conclusion, that's the we have the we can if you want to measure the fidelity of the permutation invariant state, how many local observables you need? It's the roughly speaking, it's the in the order of the n square. And for some special case, you can do better, just so linear, eventually linear. For graph states, we can also have implies a very low local measurement setting complexity. All right, thank you. And any questions?
Okay. Is there any question for Xiongfeng? Yongchen has one question.
Hi, Xiongfeng. This is Yongchen. So I have a question for you. So supposedly, if you use this kind of witness, which is tailored for symmetric states, to try to do the entanglement detections, but let's say for some reasons, the states is actually not exactly permutationally invariant. The actual states produced in the lab. So I wonder if there's a way to make it robust, make the witness robust, so that it could also tailor for, I don't know, somehow off from the symmetric subspace. Do you see a way of doing it?
Okay. I see.
You understand the questions?
Yes, I get the question. Okay, yeah, that's a very nice question. So let me rephrase the question a little bit. So basically, here we assume that your target state is symmetric invariant. It's a symmetric state. Your target state is symmetric, but in the experiment, due to the imperfection, maybe your target state is not a symmetric state. So that's your question, right? So maybe it's quite close to symmetric, but it's not far away from the symmetric state.
Exactly.
So your target state, of course, the unknown state, we never assume any property of the unknown state, right? So the prepared state can be arbitrary, right? It's always arbitrary. So in that case, yeah. So the key question is that how many local observables we need. So we have worked out that if it's a non-symmetric state, for example, if it's we call the translational invariant state. Okay, translation. So which is a bigger set than a symmetric state, right? We can still do it quite efficiently. But if you have if you say that's maybe the state is a little bit strange, like in the other forms, then for example, like GHC state, graph state. Graph state is not in general, it's not a symmetric state. We can still work out. So the key point is it depends on how many fluid parameters you have for this particular state. If the number of fluid parameters for their set of the state, if the number of fluid parameters is small, we believe that we can find some way to reduce it down to a very small number of local observables. But we don't have a general theory say that so if you have a certain amount of the certain form of the symmetry, we can reduce the local measurement setting. We don't have such kind of general results yet, but we believe that it can be done. That's a very good point.
Well, actually, I think my questions, I think my concern is the following. So in principle, you determine being a witness, you have the promise that the expectation value from, let's say, all these biseparable states have to be non-negative. Okay, but in your case, you have to work under the assumption that all these biseparable states are also symmetric.
Oh, no, we don't assume that.
So you don't make this assumption. Okay.
No, I don't. So the underlying, so we assume the underlying state is arbitrary. So let me. So the state itself, so the state you want to measure is the whole state. So basically arbitrary. It's just the target state is symmetric state.
Okay, so you make the assumption that in the optimization the states have to have this symmetry.
No, we don't assume. So basically, like in the experiment, when you prepare some state, so that state is arbitrary. We don't put any assumption on that one.
Okay, great, thanks.
Yeah. Okay. Yeah.
Okay. Due to the time constraint, so let's end this talk now. The speaker Xiongfeng again. Thank you very much.
Thank you.
Very nice talk. Thank you. Good. So let's move on to